Good. Good afternoon, Andrea. How are you?
Hi, how are you?
I'm good. Thank you very much. Okay, great. You are with us and we are streaming and we are live. I understand this is your lunch hour, so I'm not going to do a very long introduction and speech and everything else. My name is Ken, and next to me you can see Arthur here, and
Hi.
audience in the background that's joining us as well in our.
Hi, everyone.
And besides that, we have a big, huge screen in front of me where we'll be able to see stuff. So without much further ado, please do go ahead. The floor is yours.
If you just allow me to start my video, it just says the host has stopped video sharing.
Okay, I will let Arthur change that setting.
Okay, it seems like I'm the host. I should be able to share my video. Hello, everyone. Can you hear me all right? Okay. All right, so I should just start. If I could just... All right. So, hi again. What I would like to talk today is the dark side of the universe, and basically everything that's dark in the universe: dark matter, dark energy, and black holes. All these mysterious objects that everyone wants to know what they're about. So I'm just going to take you to a ride to the dark side of the universe, and I hope you will enjoy it. And again, if you have any questions, just ask me. Right, so without further ado, I just want to start with the question is about what the universe is made of. And so astronomers have actually measured the content of the universe. And if you put everything on the so-called energy and matter budget, so if you just calculate what all the matter there is in the universe and you measure all the energy in the universe, we figure out that about 75% or 70% is this mysterious form of energy called dark energy that has nothing to do with us. Then about another quarter or so is made of, so the rest of the universe is just made of matter. Now, not all the matter there is in the universe is actually matter that we actually are familiar with. In fact, most of the matter is just dark matter. So if I take this slice of the pie here, which is the total matter of the universe, about 30%, and I say how much is normal matter that makes stars, galaxies, and dust and gas, that's about 20%. And the 80% is just this mysterious form of dark matter. So if we put everything on this cosmic pie, you can see here that most of the universe is unknown. So about 70% is dark energy that we don't have any idea what is about. And then the rest of the pie is dark matter. Again, we have little knowledge of what this dark matter might be. And only 5% of this cosmic pie is made of atoms or particles that we can actually measure. And why is it important is because this is basically this 5% is the observable universe. Everything that shines in the universe, stars, galaxies, atoms in gas that is heated up and emits X-rays, all of this observable universe is in this thin slice of the pie. The rest of it, we just have to infer it through different ways. Okay, so what I'm going to talk about is just this big unknown, dark matter, dark energy, and some of the bits that are still unknown in the observable universe, which are these black holes, again, which we cannot detect very easily with our telescopes. So I'm going to start with the most mysterious and the most unknown component of the universe, which is this dark energy. And again, we don't actually know what it might be. We see its effect. So if we look at the universe and we measure the motion objects in the universe, like galaxies, we see that everything expands. Galaxies themselves do not expand themselves, but just distance between different galaxies grows further and further. So if there was a beginning, which we believe it was the beginning of our universe about 14 billion years ago, and that we call it the Big Bang. The universe was very tiny near the Big Bang, but it started to grow bigger and bigger. And we are today, present day, about 14 billion years after the Big Bang, and the universe is still expanding. But what we actually observe is that the universe is expanding faster and faster. So it's like if you are in a car and just to push on the acceleration pedal, just your car is moving faster and faster. That's what our universe is doing. It's accelerating. So there's no reason for the universe to be accelerating just because of whatever it's in it, like in terms of galaxies and even dark matter. So it must be something else is pushing the universe apart. And we think this is this mysterious form of energy, which we call it dark energy. And we have some ideas what it might be. The closest analogy to what is happening with what we know from physics is this this idea of quantum foam, which is a particles. So the space is not completely empty, even between galaxies. It's not a perfect vacuum. There's always something in it. And it's this foam of particles that come into existence and disappear. And we think this vacuum, it provides an energy, which is this dark energy, which is expanding the universe. Now, I'm not going to talk too much about dark energy just because we don't actually know what it is. I'm going to talk about something else that we have a better idea, which is the dark matter. Now, dark matter is called dark because not because it's black, because if you think of a very black object that you know on Earth, like you have a black piece of clothing, it's dark because it absorbs light. Okay, and so it's not what dark matter is. It's not black. Dark matter does not absorb light, does not emit light. If you would do any of these things, we would be able to observe it with our telescope. So anything that interacts via light, we'll be able to detect it. So dark matter is not black. In a sense, it's more like transparent. We know it's there, and we call it dark just because we don't know what it is. Okay, but we know that it should be around everywhere, around galaxies, around big clusters of galaxies, everywhere in the universe. So for example, if you take a galaxy like the Milky Way, we are living in such a spiral galaxy, so a nice galaxy with nice spiral arms. And this is what you see here is the material that we actually can observe, everything that shines with starlight. But around it, we think there's a bigger halo, as you call it, like a big sphere full of dark matter, which extends much further out than the luminous matter. Now, how do we know this? I'm going to say a few words in a minute. We also know that, so these big halos of dark matter are not just around individual galaxies, but they're around anything that is clustered of matter. So galaxies, they also can cluster together and they form big conglomerations of galaxies, which we call clusters. And around these clusters, there's also big halos of dark matter. So wherever there's light, there's also dark matter. But dark matter could also exist independent of the starlight. So it's basically just everywhere in the universe. Now, we discovered dark matter in various serendipitous ways. One way that was discovered is in the 1970s by an American astronomer called Vera Rubin. And she was looking at the rotation of spiral arms in these galaxies, like our own galaxy. And she was looking to see how, she was trying to measure the speed of rotation of the stars around the center of the galaxy. And I'm showing here two computer simulations of what we expect and what we actually see. So if you see here on the left-hand side, this is what we expect. A galaxy, the stars that rotate further out from the center of the galaxy, they should rotate slower. Whereas what we see, or what Vera Rubin saw back in the day, is that the stars further out from the center of the galaxy rotate faster. So or as fast as the stars near the center of the galaxy. You can see here, if you just compare these two objects and look at the rotation on the further side, you can see this one rotates a bit faster. Okay, so what is spinning the galaxy so fast is just the dark matter, because the stars themselves will not be able, they don't have enough mass to spin the galaxy so fast. So this is an indication. We don't actually observe dark matter per se. We can't point a telescope and detect dark matter as such, but we just see the effect dark matter has on the rotation of stars, or the motions of stars, or the motion of the galaxies in the universe. So this is how the dark matter is discovered. Of course, it's not a very satisfactory discovery, because we wouldn't stop until we actually detect the dark matter through in a direct way. And I think this may be possible in the next few years. We have lots of experiments on Earth and in space which may detect dark matter. Okay, now I am actually a theoretical cosmologist, so I do simulations on a computer. So it's really fun. You can actually put this dark matter on a computer and run a simulation, and you see what happens. And this is how we actually can explain these dark matter halos around galaxies and around clusters of galaxies. So this is a snapshot. This is an image from a computer simulation with the universe just filled with dark matter. And as you can see here, there are these filaments. The dark matter is not distributed homogeneously. They're always the same throughout the universe. It just clumps into like rivers of dark matter. And then when these rivers cross, you have like these big dark matter halos, which host the galaxies. So we believe that the whole universe should be crisscrossed with these rivers of dark matter. Now, if you don't believe me, I can show you actually a simulation that forms this dark matter. So at the beginning, if I just stop it right now, near the beginning is just the beginning, you see a very smooth distribution of dark matter, as we think the universe was in a pristine state near the Big Bang. Everything was pretty smooth with just some tiny fluctuations here and there of dark matter in the universe. Now, the dark matter feels the force of gravity, so we will just clump. If you let the dark matter evolve, it will just feel the force of gravity, it will attract more dark matter around it, and will form these structures, this dark web filaments of dark matter in the universe. So this is what is happening here in this simulation. So we start the simulation near the Big Bang, and we let it evolve until the present day. So about 14 billion years of evolution of the universe. And you see at the end, we retrieve these nice filaments of dark matter with big halos around it. So this is just showing the dark matter in this big halos, you will form galaxies and solar systems and planets and everything else. All right. Now, dark matter, you would think the dark matter is this esoteric thing that just out there in the universe, but it's nothing to do with us. In fact, dark matter is everywhere. So if there's particles, the dark matter is made of like particles, this should be even around us as we speak now. So we are inundated with these dark matter particles. Of course, we can't feel them. We can't actually see them. It's just this river of dark matter going through us. It doesn't interact with us through any force other than gravity, and the force of gravity here on Earth is very weak, so we wouldn't be able to actually feel it, and it doesn't do any damage with us these particles going through us. All right, but there's lots of dark matter particles, so even in your room that you are there's billions and billions of dark matter particles going at every second in that room. Much more dark matter than atoms in the universe. Okay, now I want to go to the next part of the dark universe. I'm going to talk a bit about the black holes. Now, black holes are part of the matter in the universe, which is not dark matter, is normal matter. And we actually know a bit more about black holes, and we know how they form. And we know more about the physics of black holes. So one way to form black holes is when you have a star which explodes, you have to have a star like more massive than the sun. Our sun will not turn into a black hole. Our sun is a very regular star, but if you take a star which is much, much more massive than the sun, it will burn its fuel very quickly and will explode and will turn into a supernova. and the remnants of that supernova would be a black hole. Now, in this image here, you see a galaxy and a supernova. And if you're lucky with the telescopes, you might find a supernova, although they're very hard to find, but there's lots. If you have a survey of a big universe, eventually you will find some supernovae in your lifetime. So this supernova is an explosion of a single star, but in that instant of an explosion, it's so bright that it has a brightness just as bright as the center of the galaxy for a fraction of a second. Okay, so these points of light, so if you take a star and you explode it, the explosion will expel a lot of fuel that was inside the star, but what remains at its core. So after all this gas is expelled into the cosmos, what is left is this little nugget, which is a very dense form of matter. And because it's so dense, it doesn't let any light escape. So this is the reason why it's dark. It's actually black, not because it absorbs all the light, it's just black because it's like basically a hole in the space-time. It's just, we can't see anything in that hole. Okay, now there's matter inside the black hole, but the space-time is very distorted. So because it's so dense, it's so concentrated, it's basically shrinking, distorting the fabric of space-time. Now, this is an image of a black hole, an artistic image, but you can see here around the black hole, there's a lot of luminous matter, and this is like just normal matter orbiting the black hole. It still hangs around and orbits. Now, we do observe black holes. We'd actually see the process of explosion of a star into a black hole, but we figure out the process. So this will be like a timeline. You have a star like more massive than the sun, for example, and then it starts exploding, expels the material, and the inner part of the star are collapsing and forming a black hole. And this is an image, a video here of the stuff that's accreting. We call it an accretion disk. So in the center of this movie, there's a black hole, which we can't see, but all around it, you can see a swirling form of matter. And this is as we call it, an accretion disk. Everything that's been expelled, but still hangs around, and it rotates around the black holes. I just run this again. You can see a lot of dust and gas around the black hole. And it's a very violent region of the universe. You wouldn't want to be there. Okay, there's lots of radiation from this gas that it's circling around at very high speeds. You can also, if you saw the previous video, there's also a jet. Sometimes these black holes with the very massive, when the material accretes onto the center of the black hole, not only rotates but also collimates, and it goes into a jet outside. It could be bipolar jet, so it can go in both directions as well. Sometimes we can see these jets pointing towards us, towards the Earth, and it's really interesting and fun. And this is actually how some of the first black holes were detected, not because of the measuring the black hole per se, but just seeing this very bright material around them. Now, what you might ask, what happens when you fall into a black hole? As you can imagine, nothing fun happens. In fact, the black holes have this powerful tidal forces that basically shred any object apart. So basically you will get spaghettified, you will get turned into a spaghetti. And this is what happens to a star, a poor star that goes around this black hole, and material will just get shredded to pieces, and the material goes into this storm around the black hole, and if it's powerful enough, it will also be ejected into this jet. So you can see it again. If a solar system, for example, ventures very close to a black hole, it will be shredded apart. The star itself will be shredded apart, and all the material from the star will be raining onto the surface of the black hole. Some of it will fall in, but some of this will just orbit around the black hole and even power a jet. Okay, now this will also happen with people. You know, if you sink into a black hole, let's say if you go with feet first, your feet will be elongated. So you basically be turned into a spaghetti. And I'm sure you don't want to do that. Now, we also know that galaxies like ours, for example, have big black holes at the center. So I talked about a black hole that forms from an explosion of a star, but black holes can also grow in time, but just secreting this matter around them. So they become very fat, and we call it supermassive. Now there's a supermassive black hole at the center of our galaxy. And again, we can't observe it with a telescope, but we can see the damage it does around it. So if we see some stars, here's a star orbiting, and you can see it's orbiting around some piece of empty space. Okay, there's not an empty space, there's just a black hole. And this star feels the gravity of the black hole. And instead of just going on a straight line, it goes does this ellipse. And this is how we know there's something there. And we can, from the motion of the star, we can actually infer how massive this black hole should be. And we know that in the Milky Way, it's about a few million solar masses. So a few million suns just collapse into this tiny single point in the center of our galaxy. And if we show it again here, you can see there's lots of stars orbiting in the center of the galaxy, and they all feel this effect of the black hole. Now, very recently, just a few days or a few weeks ago, there was a first image of the black hole in the Milky Way, done with a series of powerful telescopes called the Event Horizon Telescope. And again, they're not observing the black hole, they're observing the material around it, but also the shadow of the black hole on this material. So this is a really spectacular image. We can actually observe deep at the center of our galaxy, a tiny black hole. And I want to also say a few things about merging of black holes. Now, what happens when two black holes come together? Of course, they would feel this force of gravity. And they could, if they get very close, they would spiral onto each other. And if, let's say, if you start with the big black hole and the small black hole will just merge onto the big black hole. So again, here's a movie here, two black holes. There's these dark centers here. You can see the distortion of space-time around them. And what happens is the black holes start moving slower, but then pick up the speed, and they will spiral in. The closer they get, the faster they spiral onto each other. And at the very end, they merge. They just become one huge black hole. And then it stops, and then you don't actually see much. It's again, you'd see this empty region of space with some slight distortion because of the force of gravity. Now, how do we actually, again, we don't actually see this happening. This is, again, is a computer simulation of what we think it's happening. Now, but we actually have detected in this process, because of the distortion of the space-time, there's these ripples in the space-time, which are called gravitational waves. And these gravitational waves can arrive onto Earth. And we have experiments on Earth that we could pick up these gravitational waves. And I'm going to show you in the next video how the first detection of a gravitational wave from the merging of two black holes. And what you're going to see here, I'm going to you might just listen very carefully. You'll see some sound. Okay, so I'm just going to play it again. So it's a very deep sound at the very end, and there's like a slow vibration, and towards the end is a high pitch. This is when the black holes start to merge with each other, spiral very fast, so that they have a high frequency. So that there's like, and at the end is like a little chirp. Okay, this is when the black holes merge. So I'm just going to play it again. This is happening very fast. You see here the time in seconds is less. This is happening in less than a second. This. Okay, so Now, the thing is that we might get it wrong. These gravitational waves are very, very weak. So we might get confused with like some waves or, you know, any distortions that happen here on Earth. So if you, for example, if you have a truck going on the street, that could also fool your experiment and think, okay, I detected something. So what you see here, there's two experiments. So this experiment is done in parallel, different parts of the Earth. They should not have any connection with each other, and they both detect the wave at the same time. Okay, so basically, at the very, very far away in the universe, there's two black holes merging, and the gravitational waves take, you know, billions of years to travel to the universe. They hit the Earth, they hit our detector in two parts of the Earth at the same time, and this is how we detect them. Now, they're not actually sound waves per se. This movie is actually turning the sound waves, the gravitational waves, into sound for our ears to actually pick it up. So it's just it's called a sonification, but you get the idea. The gravitational waves are detected. Okay, so that concludes my short trip on the dark side of the universe. I hope you enjoyed it. And I'm looking forward to have a chat with you if you have any questions.
Hi. I put the question in the Zoom chat, but how frequently are we discovering more of our universe, like just in general? Like you mentioned there's dark energy and dark matter. How frequently are we finding out what that is?
How frequent?
Yeah.
You mean how many experiments we have?
Yeah, it's like throughout.
So the dark matter and dark energy are there. We can always devise an experiment to try to measure it. Okay, so as I said, these dark matter particles are going on through our bodies as we speak, right? So if we have an experiment that the problem is not that they are there, that the problem is how to actually detect it. Okay, and this is the difficulty. Now, in the beginning, we had no clue how to devise an experiment to detect dark matter, but with time, people, physicists and astronomers got smarter and smarter, and they devised lots of experiments. So as we speak right now, there's lots of experiments around the Earth trying to figure out to measure dark matter. So there's like experiments and deep in the mine, you know, whether deep at the bottom in like few kilometers underneath our Earth surface, just to minimize the noise from other stuff, just to detect this dark matter particles maybe hitting a detector. There've been experiments in space, you know, just above the surface of the Earth, trying to pick up some, if the dark matter, maybe they don't interact to us, but maybe they interact with each other, like this dark matter particles colliding, and maybe they would emit some gamma rays, for example, some very energetic radiation. And we should be able to detect this aftermath of dark matter annihilation in the form of gamma rays. So for that, you need to set up your gamma ray detectors on Earth. Yeah, so there's lots of experiments. None of them has turned a conclusive detection of dark matter as we speak, but there's still hope. In terms of dark energy, I think that's much more difficult to actually detect. We see again the expansion of the universe. We think it might be this foam of quantum particles, and you know, quantum physicists could actually detect the vacuum. They have experiments to detect the vacuum in the lab, so that's not a problem. We just don't know for sure whether the dark energy is that form of vacuum that we see here on Earth. It might be something else. I hope it answers your question.
Thank you, Andrea. Thanks for a very interesting talk. I apologize in advance for like maybe a weird or silly question, but like if I understood correctly at the beginning of your talk, so we haven't really measured like we haven't had any direct measure of dark matter, and you're saying that measuring dark energy is really difficult. And if I understood correctly, like dark matter is there because it has to be there. It has to be there for kind of our models, our understanding of, you know, the universe to be true. And like how, I kind of want to ask, like, how likely do you think that those experiments that are being put together right now will not turn up anything? And will that mean then that our understanding of gravitation and of the Big Bang, so the history of the universe, is wrong or not accurate?
Yes, I think you're asking the right questions. Obviously, so I mentioned Vera Rubin discovering dark matter in the 70s, and actually we have more evidence even before that. In the 1930s, there was this Swiss astronomer called Franz Zwicky, and he first figured out, again, from the motion of galaxies in clusters, there should be some dark matter. In fact, he coined it Dunkelmaterie in German. So we actually know for about 90 years that dark matter should be there, and we're getting a bit anxious in a sense that we can't actually detect it, even though there's been lots and lots of experiments. And yes, it is a very difficult thing to measure. It's, you know, I'm not trivializing, but it is also an issue that, as you say, maybe we don't have the right physical model for dark matter. Now, in counterpart, I talked about this computer simulations with dark matter particles, but it could, you know, there's an alternative model out there that says, well, there's no dark matter, but as you said, maybe we don't actually understand the force of gravity very well. So, you know, that Newton's force is like the product of the two masses divided by distance squared. So there's a distance squared, there's an exponent there. But if you play a bit about with the Newton's force, change a bit the exponent so that, you know, it's 2 around us here on Earth, but it changes to a different exponent if we go on large distances where we see this dark matter. So if you play with a variable, it won't be a Newtonian force anymore, would be, as we call it, a modified Newtonian gravity, or MOND. And people have been playing with that physical model, and it actually explains this rotation of galaxies. It's Vera Rubin, so it explains the data that Vera Rubin was observing very well. So MOND is a good alternative model. MOND can't explain everything, so we're trying, when we get a model, we have different tests. So does it explain the rotation of stars around the galaxy? Does it explain the motion of galaxies in a cluster? Does it explain different things that we observed and our indication of dark matter? That your model has to tick all the boxes. They have to explain everything. If it doesn't do that, it's not a good model, right? So we don't actually know whether MOND could tick all the boxes yet. And certainly there's some indications that some observations are not very well explained by MOND, but it's not the definitive word on this.
Okay, thank you. And a kind of follow-up question. So I've heard that gravity is generally, like in general, is kind of a problematic force that, you know, we haven't found a way to unify it yet. So to find something that kind of links gravity to all of the other forces that we are explaining, is that linked to this problem somehow, or?
Yes, it's true. I mean, gravity is a very weak force, and it's about 40 orders of magnitude weaker than electromagnetic force. So this is why basically we can't actually feel dark matter, right? If it depends on the mass of, if there's many ifs. If the dark matter is a particle, and if it's a very massive particle, right, then it should have been formed very early on, before other parts of the other types of particles. So it should probably, you know, we need to modify our physics a bit to actually accommodate, because, you know, if you form early on, they form closer to the Big Bang, right? When the forces would become unified, right? You know, the closer you go to the Big Bang, you first unify the electromagnetic force with the weak force, that's the electroweak force. You need a lot of energy to do that, and people have managed to reach that energy here on Earth with CERN. But it's a big step. If you go even closer to the universe, you could unify the electroweak with the strong nuclear force, okay? And then if you go even closer, unify these 3 forces with the 4th force, which is the gravity, okay? And that's called the GUT era, the Grand Unified Theory. And that's very, very, a fraction of a second after the Big Bang. Well, I actually don't know whether the dark matter is, yes, it goes into the closer we go to the Big Bang, the closer we go into the here are the dragons. We don't actually know much what happens there in terms of like generating these particles. So it is possible that dark matter has something to do with the early physics of the universe.
Okay, thank you.
But the timing of it depends really on the mass of dark matter particle, right? If it's light or if it's massive, it changes the whole story.
Okay. And last but quick question, hopefully. So you mentioned that at the center of our galaxy and also other galaxies, there are these supermassive black holes. But are these the things that are holding our galaxy together? So is the gravitational force what's basically attracting all of the spiral arms and everything, or is it just not? Like, how is it linked to the history?
Yes, it's more like an organic thing. Like you think of a galaxy as an organism. It grows from a tiny seed, and everything grows. The black hole grows at its center. The spiral arms grow. Now, in terms of if you put some numbers for our galaxy, it doesn't have to be for other galaxies, but for our galaxy, the total mass of a galaxy is 10 to the power of 12, right? So what is it? Is 1,000 billion solar masses. If you take 1,000 and then another billion, 1,000 billion suns put together, that's the total mass of our galaxy. It's huge, right? Now the supermassive black hole at the center is massive, but not as massive as that. It's just a few million, right? So there's orders of magnitude. So it's not so important on the grand scale of the galaxy. However, in some other galaxy, there's more massive, supermassive black holes. So it's kind of like an ecosystem of black hole growth with the growth of a galaxy. So the black hole certainly affects the inner part of the galaxy. Obviously, you see this big storms, these tornadoes of matter around the black hole. There's these powerful jets. They will do a lot of damage in the center of the galaxy. For example, you can actually have life very close to the center of the galaxy just because of this powerful radiation, which is destroying any hope for life. So it is a kind of a local ecosystem around the black hole. In some other parts of the universe, this supermassive black hole do a lot of damage and actually change the composition of, we see that in centers of clusters of galaxies. You have supermassive black holes that have these powerful jets, and that actually changes the physics of the gas, even at very large distances from the center of the cluster. Yeah, so in a sense, it's a balance of how big is the black hole and how big is the host galaxy.
Okay, thank you.
Yeah.
Yeah, I got one question. When you're mentioning about the black holes, you got these jets shredding and shooting it out. Are you actually monitoring the shooting out and where it's going and what's happening?
Yes, we don't actually see, so that's a nice movie, but obviously we actually can't see that in real time. So what we actually see, we see the light, and we have we can extract information from the light around the black hole. So for example, not just imaging, but there's more detailed information we get from spectra of atoms. So all this gas that's orbiting, there could be hydrogen atom or some other type of atoms, and they have some specific spectral lines. And the faster they rotate and the faster they emit light on certain wavelengths. So there's a lot of information just extract from the light. So this is how we know that it rotates, we know the composition, we know the speed, and so on.
But just like, for example, if like, say 100,000 million planets have gone through the black hole and it's been spat out, is that now eventually going to be forming new planets somewhere else? Or is anything?
Yes, the material, if you mean the jet.
Yeah.
Yes, it is. Yeah, it could be like a fountain, right? You get material coming in and then going out, raining. So if you get the material expelled and goes in the outside of in the outer parts of the galaxy, that gas, when it cools, you have to form planets. You have to cool that gas. You can't form anything when the gas is very hot and emitting X-rays and everything. You have to let it cool a bit. And the gas cools rapidly because it's called a radiative cooling. It radiates energy and cools. So you need to form planets. You get to get that gas very cold and then attract dust as well. To form the planets, you need like an Earth, for example, the Earth is not made of just hydrogen gas. You have to have iron, carbon, and so on, all the other heavy elements to form and you also need water, right? If you think of a planet which is habitable, so you need, besides hydrogen, to have oxygen, right? And that oxygen has to come from supernovae. Yes, I mean, it's a good question. I don't think this process has been actually detected in real life, right? When we look at the universe, we see a snapshot of what's going on. We don't actually see it happening in our lifetime. The timescales are very long, right? So we did see different snapshots, a galaxy here with a jet, a galaxy here with some planets. And so we kind of put the pieces of the puzzle together.
But you're currently like storing those snapshots, and hopefully eventually over time, you might see something happening there, right?
Yes, yes.
Cool. Thank you.
Okay, I'm back. I was sitting on the sidelines listening to all of this. Thank you very much for that. I actually had a question, but I think Arthur asked it because it was more related to all of the work that you were doing. Obviously, we had all the theories and all of the formulas from the previous centuries about mass and atoms and all that kind of stuff. So the question was, are you seeing, or are you likely to see any changes or needing to adapt or tossing out any of those theories or equations or stuff like that? But I think that one was asked and answered by Arthur.
Yes. Sorry, my battery is running low. I just got all right. I hope I could answer the question in real time. Yes, I mean, we obviously understand gravity. Gravity has been already modified by Einstein in so-called general relativity, and that theory is very well established, and we actually can check that theory with this merging of black holes. We know the general relativity works. Now, there's pieces of the theoretical understanding that's still missing. So, for example, we can't connect quantum physics, which rules the microscopic world, the world of particles, the atoms and interior of nuclei, with general relativity, which tells us how objects move on the larger scale. So the macroscopic with the microscopic are not well.
Okay, so I think that pretty much ends the webinar. For anyone watching, thank you very much. And you can watch the webinar once again on Facebook as well, where it will be on the Makerbox page. Thank you for joining, and have yourself a wonderful evening.